Thank you, Dominique. Well, my talk will address, let's say, higher atmosphere observation, what we call limp sounding, but also some observation above the Earth atmosphere. Well, I have a lot of caveats. This academic session celebrates 50 years of research, and it is just impossible to summarize in 30 minutes. I have some hypotheses. Most people here are interested in science. Not all of them are experts in the field of remote sensing, so this speech will be a tool to give you a flavor of what is atmospheric remote sensing when looking to the limb. And I have also apologies to past and present scientific colleagues not being able, because I will not be able to present all their contributions. I would like also to underline that most of our achieved work, at least on the experimental part, would have been impossible without a lot of people at the Institute, engineering, IT, but also accounting and program management, thanks to all these guys. Well, space aeronomy, with a question mark on space. Why? Because it's one of my favorite distinctions. Space means a medium to be investigated, like presented by Johan de Keyser, but also, for us, space is the highway to atmospheric remote sensing. Why highway? Because at least 5 points are clear. The Earth has a curvature. You cannot look behind the horizon. Second, if you want to measure everywhere, with, let's say, a revisit time from one day to a few months, you have to be fast. You have to do that from space, and of course, we have to remember that 70% of the Earth area is covered by water. Remote sensing to the limb is also a synonym of high sensitivity, because you have longer optical paths, and with only a few molecules added along the optical path give some effect. Also, in limb sounding we have different sounding geometries and different local solar time that may impact the photochemistry of the atmosphere. And finally, of course, when looking to the limb, we will have a high vertical resolution. Well, coming back to the 90s, there was this famous Atlas flight with an heritage of a lot of instruments from Space Lab, and you recognize, of course, Dirk Frimout. And at that time, it was really a glorious time, because there were 4 instruments in which Belgium was involved. The SOLCON instrument, the SOLSPEC, which was a measurement of the solar spectrum irradiance, and typical, more specific to atmospheric physics, we had an occultation instrument, the Grill spectrometer in collaboration with France, and also the Halley measurements of the first detection of deuterium in the thermosphere and mesosphere. Well, SOLSPEC, this is SOLSPEC as a long heritage, and presently we have a SOLSPEC instrument flying on the International Space Station. In a few words, it is, let's say, what I would call an absolute instrument. It's an absolute radiometer, and it measures not only the solar constants, which is about 1300 watts per square meter, but it makes a spectrum, and the solar constants doesn't vary so much, but you may have a large variation in the UV and in the infrared. I guess that SOLSPEC will become, within a few years, really one or even the reference spectrum for solar irradiance, and it has been prolonged at least till 2017. And he is presently under the leadership of David Bolsey in our institute. But back to some generalities about limb sounding. Well, a few words. The king method of limb sounding is occultation. Occultation, you can do that, you can experience that when looking at the sunset on above the sea. You see a reddish sun, so it has a color, let's say, or the atmosphere has absorbed the blue part, and also the intensity is much lower. So it means that you have already an information by looking at the occultation of some line of source through the atmosphere. The second important point in occultation techniques is that you have a property of self-calibration, which means that even if your sensor or your detector is varying along the time, what you do is you measure, you compare a measurement through the atmosphere with respect to the measurement above the atmosphere, and you divide the first one by the second, and you get an absolute quantity, which is the optical thickness. So it's a very interesting property for as an experimenter to have a self-calibration. Finally, you should not be confused that we measure, but the technique itself just produces a signal. And after that, you have a lot of difficult mathematics, which we call mostly inverse problems, like in seismology. We have a vertical inversion to distinguish the contribution of several atmospheric layers, the so-called onion peeling. So this is our favorite vegetable, and we use it also in spectral inversion, where we have to distinguish at a given wavelength different constituents contributing and interfering with each other. Well, so three concepts. Now, something more concrete is it ORA. ORA was the occultation radiometer, and it was on board of Eureka, the European Retrievable Carrier. It was put in orbit by the shuttle and retrieved about 1 year later. And on board of this instrument, we had a radiometer with a large field, 2 degrees, at 8 wavelength, and this was under the PI-ship of Etienne Harris. And basically, we were observing the full solar disk occultation, collecting the signal at different wavelengths on the photodiodes. And this was done from the UV to the near-infrared, and it led to a very successful publication. Typically, for such an occultation experiment, depending on the orbital inclination, we were able, during 1 year, to scan, let's say, a geographical domain spanning from 40 to minus 40 degrees. And this was due to the, let's say, a non-optimal inclination of the orbits. But you understand already that a lot of measurements could be done. And as an example of results, this was we published a climatology, or one of the first climatology of the second ozone maximum. In the mesosphere, there is a second ozone maximum. And we could measure it thanks to the very high sensitivity of ORA, because we are measuring the full solar disk. Well, something more sophisticated now. GOMOS on Envisat. Envisat was the biggest satellite ever built by ESA to observe the Earth. It was launched in 92. On board there were 3 atmospheric instruments, GOMOS, Sciamacchi, and MIPAS. We have been deeply involved in GOMOS. Here you see the size of people with respect to this huge satellite. And GOMOS has been operated with advice from 3 expert laboratories from Finland, France, and ourselves. And again, it's the same occultation principle. You observe a spectrum outside the atmosphere, and a little bit later you will see some absorption at specific wavelength, and you will get information about the absorbing species. Well, this is a typical example we could get from the occultation of Sirius in 2002. This is the full Sirius signal above the atmosphere, and as the star settings occur, you will see, for instance here, ozone absorption in the Chapuis band. So it is the typical signal we can observe. This is a schematic of the GOMOS instrument. I don't want to mention that, to develop too much about that. It's a very tricky and complicated and very expensive instrument too. Well, with star occultations, one of the advantages is there are much more stars than the sun, and Sun, you only get for each orbit a sunset and a sunrise. Each time you have a bright star, you can observe it, and this is one day of GOMOS measurements. Well, typical results we were able to produce with the colleagues of GOMOS was a very large, a very extended distribution of the ozone distribution, not only the well-known stratospheric ozone, but also here the mesospheric ozone, and its semi-annual oscillation. We have a long tradition of aerosol studies, stratospheric aerosols, showing, let's say, also occurrence of polar stratospheric clouds at the South Pole. We had observation of NO2 layer, intrusion of NO2 layer from the from the mesosphere into the upper stratosphere due to subsidence. And our group has, for instance, identified polar stratospheric clouds in GOMOS measurements and was able to measure the descent rate in the vortex of these clouds that are involved in the ozone hole problematics. Well, when you combine and when you work with stellar data, you accept to have a very low signal-to-noise ratio. And so one of the things you want to do is to increase this signal-to-noise ratio by using statistics actually. And doing like that, you are even able to distinguish the OCLO presence, and we were able to discover OCLO layer in the equatorial region. So not only confined in the polar region at the time of the polar the ozone polar conditions, but also to identify this OCLO layer, which is actually a proxy for the CLO. Well, using the same technique, we have been able to identify the sodium absorption at 590 nanometer. Of course, you see the scale here. It's in the 10 minus 3. It's a very, very small signal. And after processing and validation, we were happy because we could compare our GOMOS sodium measurements with ground-based LiDAR and with another instrument, Osiris. I like, so this is a climatology we have produced for the sodium with some semi-annual oscillation at the equator and a polar oscillation at the in the polar regions. You have to know that sodium is a product of meteorite ablation. So I think this is a nice example of how fundamental research can almost unexpectedly feed applied research and be useful. Because a byproduct of this climatology we published was a strong interest by several laboratories because you know, big telescope, the limitation in their angular resolution is due to atmospheric turbulence. And they can use what they call adaptive optics. I don't want to explain that too much, but basically it's to correct the wavefront that comes into the telescope. And for that they need a reference. But there are not so many references if you want to look at faint objects. So the idea was to shoot a laser light up to 80 or 90 kilometers to make, let's say, an artificial star, and to collect the light back, to analyze it, and to drive the telescope to correct for turbulence. Doing so, you can achieve on ground angular resolution that are compared with Hubble telescope. So this is a typical example of the use of, let's say, fundamental research, the mesospheric sodium layer for applied astronomy or optics. Well, we have also collaborated to ACE Maestro, very nice Canadian success in the field. This mission had also 2 Belgian imagers, and I think these imagers were probably one of the triggers to think to other missions I will speak about later on. And you can see the power of imaging. This is a solar disk, and with the polar stratospheric clouds crossing it, or even with a bimodal structure, which is quite different to, let's say, a convective clouds at the equator. Well, we are not only looking to Earth with remote sensing. Mars is also a very interesting domain where we have been involved. And I want to mention MEX for Mars Express, PICAM, collaboration between the Institute and the Service d'Aéronomie, not must know. And this instrument is still working. You know that Mars has, of course, strong importance for maybe for habitability. And we were able to produce papers about clouds, ice, and dust climatologies on Mars. An issue is also to derive a good ozone climatology, because ozone is, of course, important to understand the UV level at the ground on Mars. Well, an heritage was Venus SOIR on Venus Express. I say heritage, it was also an instrument, SOIR was an instrument in the infrared with a very high spectral resolution. It was initial spectrometers with some AOTF already at the time. And this instrumentation has mainly been developed in our institute by our engineering team. And I think it was very, very nice work and highest technology available. This instrument is still working now in a very aggressive environment, you know. So a lot of data have been produced by SOIR Venus Express, also in solar occultation experiments, and in particular, accurate determination of the CO2 vertical concentration profile and temperature profile have been done, together with long-term variation of, let's say, aerosol or haze, and observation of unidentified absorption lines. Heritage of SOIR, NOMAD. NOMAD is probably one of the most ambitious experiments ever built, instruments ever built at the in your institute. It will be embarked on ExoMars TGO 2016, and it will combine let's say, some SOIR-like instrument in the infrared for solar occultation and also for nadir observation, together with UV visible observation by Open University. Again, the involvement of our institute is maximal in this project. The PI is Anne-Karin Vandal, and a huge contribution also of our engineering team, with a lot of Belgian participation. Well, the objectives are related, of course, to the presence of methane or not on Mars, but also to several isotope and specific molecules that could be detected by the SOIR spectrometer. In parallel to that, we also sustain a modelization effort by, well, I have to go faster now. What is my limit, Dominic? 10 minutes, okay. Back to Earth. There is a dramatic decrease to the number of vertical atmospheric sounders, in particular since NVSAT disappeared in 2012. I have a question. Do we enter into the dark age of atmospheric limb sounding? The answer is no. We have a potential solution, which is a full mission proposed by the Institute, which is called Altus, and which is basically a limb sounder. You know, in the year 2000, there were a lot of instruments available. They almost all disappeared. And we are very close to a situation where the recovery of ozone we will not be able to measure that. So, it's a long story, and I don't want to bother you with that. We expect to be approved or rejected, we don't know, in April 2015. Although there are strong everywhere recommendations to have to feel an urgent need for mission to observe high resolution vertical profile of the atmosphere, in particular, of course, for the ozone. Well, we will make use of several innovative techniques. Instead of using the sun as a light source, we will look at the bright limb. So it will be solar light scattered at the limb, offering a much higher coverage. We will make use of, let's say, imaging, and to perform the spectroscopic analysis, it will be done by what we call acousto-optical tunable filter. This kind of device are not electromechanical, only electronically driven, and they have, let's say, for medium resolution, they have very interesting properties. But probably the most innovative aspect of our project for Altius is the fact that on a Proba class satellite, a microsatellite, we would be able to play with the agility of the satellite and to rotate it. For instance, we will measure in the limb, and then we will, at the terminator, observe a sunset, then going back into the eclipse, looking at stars and planets, and maybe the moon, and coming back, having a sunrise and a night. So it is the capacity to be alone on board and to have a very agile microsatellite that allows this kind of scenario. I will not spend too much time on the several more scientific applications. This is just the coverage we may expect to get over one day. And I will not discuss the capacity of the instrument as we have it. It is indeed mostly focused on ozone studies. To give you a flavor of what we expect to achieve with such satellite, it will be to what we call assimilate. Assimilate means to combine measurements with a model to interpolate everywhere where you don't get observations. And we claim that with Altius we are able to achieve the same quality of interpolation that is done with probably the most performant sensor still alive. So in a nutshell, Altius is a limb sounder spectrometer, and it will observe images of the limb in different wavelengths from the UV to the near infrared, and it has ozone profiling as its main objective. Why do we do Altius? Of course, because global change is impossible to assess without stratospheric measurements. As I told you, there is a dramatic decrease in the number of available sounders. We want to promote new technologies of observation, and of course, we have many potential communities interested by ozone data. This is an artistic view, and I hope it will be like that too. And now, to finish, something completely different. Picasso. It's not a toy, it's a picosat, let's say 30 centimeter. This is a nice mock-up of it. And it has been recently approved by ESA as an in-orbit demonstration mission. Well, one of the questions is, maybe this is the future of remote sensing. We don't know yet. It should be affordable, should be fast, evolutive, and a little bit risky, but this is the beginning. So our objectives are, let's say, to demonstrate something. We will not operate such a satellite like a big instrument like Altius or GOMOS or Skiamaki. No, we want to demonstrate science in a CubeSat mission. It is not only an academic toy, it is something that can be used or that will be used in the future. And to do that, we have on board two, let's say, experimental payloads. We have a sweeping a Langmuir probe, already explained by Johan, and we will have vision, which is a visible and near-infrared spectrometer. It is Picasso is a consortium under ESA coaching. We are the prime, and we will interact with English and Finnish partners and Centre Spatial de Liège. And vision itself, we just try to demonstrate that we can do ozone profiling in solar occultations a few times a day, and also that we have good techniques to analyze refraction refractive effects and to derive temperature profile of the upper atmosphere from that. So, artistic view again. Normally, we should fly around 2016, but you know, in space business, you have to be patient. And I will close my talk by some personal statements about space aeronomy. Basically, atmosphere is three-dimensional. Of the three dimensions, the vertical is probably the most important, where things are varying the fastest. How to measure constituent profiles? If you want to do it in 3 days, over a grid or a mesh of 300 kilometers by 300 by 1 kilometer resolution, there is no other way than using space. So you need missions observing the atmosphere and looking to the limit. In the last 50 years, I think our institute has reached a level of excellence in limb sounding for Earth or planetary atmosphere, from ideas to instruments, from data processing to retrievals, and from climatologies to modelization and data assimilation. So, we also need space-qualified workhorse, which means really instruments that will at least survive for 3 to 5 years in space. And this is, of course, extremely difficult to achieve and very expensive. You need space-qualified constituents, you need components, you need a lot of testing and environmental tests. But also, and you need this kind of missions to ensure long-term series and data continuity. But in parallel, I'm convinced that we also need technology development and laboratory team mice to explore new observations techniques, because it is probably the future. It will be cheaper and easier to implement. So I'm convinced that a scientific institution also needs research and development. We have to try new things, even on the experimental point of view. For people that think that we are expensive, this is not so evident. We are cheap, because a 100 euro mission over 10 years means €1 per year and per Belgian citizen. And of course, we are very happy to support Belgian industry in parallel to our scientific objective. Finally, I think the true challenge for us in the next 10 or 20 years will be, are we reactive enough? Are we fast enough with space missions? And typically, climate change can be, let's say, confirmed or detected with a good level of confidence over a typical period of 10 years, let's say 2 or 3 IPCC reports. So it means that we cannot spend 10 years to develop missions. And probably my answer is Altus may be higher, but Citus should be faster. And Fortius, I don't know. So thank you for your attention.